Hello students. So we have only just 3-4 days for JEE advanced exam. So in that point of view, so let us discuss some important questions or some important reactions from chemistry. So here one of the question which is already placed in one national exam. So first of all, on reaction with the methyl magnesium chloride and followed by reaction with the HCl. So here in this case, first CH3 minus attacks on this carbonyl carbon. So here by reacting with the methyl magnesium chloride, so we'll get the OH and here hydrogen and then CH3. So here now in reaction with the HCl, so first here protonation of this OH group takes place. So and CH3 here, this is converted to OH2 plus. Now it is a good leaving group, so you'll get the carbocation. So ring expansion takes place because here 4-member ring adjacent there is a positive charge. So by ring expansion we'll get the just here 6-member ring. That means here 1, 2, 3, 4, 5. Just here 5-member ring. So in this case, first carbon, second carbon, third carbon, fourth carbon, and fifth carbon. On the first carbon, there is a methyl. Now here, between 2 and 5 carbons, second carbon carries a positive charge. Again, there is a hydrogen on the first carbon. By the H minus hydride shift, we will get the very stable carbocation tertiary. So now it is attacked by the Cl minus. So the product is CH3 and Cl. So answer is D. So first here reaction with Grignard reagent, then reaction with the HCl, ring expansion takes place and the H minus transfer takes place. Finally we'll get the stable carbocation. So here it is also one of the reaction intermediate, it is also one of the reaction intermediate. Here it is also one of the reaction intermediate. That means here it is a 4-member ring and plus it is also one of the reaction intermediate. Okay, that's it. And next second question. So it is based on the epoxidation process. If R equals to H, here alkoxy alkene, your peracid, benzene is a solvent, here R is a COET, here R is a H. So here in this case R is COET means, for suppose I am writing above the plane O, R is a C double bond O E T. So this one reaction with the peracid, okay, and reaction with the peracid, here hydrogen. So next here in this case oxygen, yes, C double bond O, here pH, it is a peracid actually. Okay, in this case, so this oxygen is transferred to this alkene, so we'll get the epoxide, C double bond O, here Et and this oxygen. Okay, so actually here the stereochemistry is different. In this case it is above the plane, now it approaches from below the plane, so you will get this oxide, the epoxide formation from the below the plane. Okay, so actually here this one involves a cyclic transition state. Okay, it involves cyclic transition state. If R equals to H, that means here in this case OH. Okay, OH. So here double bond, here carbon, here there is a phenyl. Okay, and next here in this case oxygen, here there is oxygen, here there is a hydrogen. So first of all in this case, okay, so here in this case so actually here this peracid for this compound approaches from the plane, that means here above the plane. So here in this case here that OH present above the plane, so this peracid also approaches from the above the plane. That means here because of the main reason is hydrogen bonding interactions, a partial positive charge, a partial negative charge, because of the hydrogen bonding interactions that approaches same plane. So here the epoxide formation from the same plane actually. Here in this case here there is no hydrogen on this group. So that's why here that parasitic approaches from the below the plane. But in this case, parasitic approaches in the, that means above the plane, because here OH also present above the plane. So first of all here, that parasite is attracted towards this compound with a hydrogen bonding. Okay, so hydrogen bonding actually here is taking place above the plane. So that's why this oxygen also approaches to the alkene from the above the plane. So the main reason is the hydrogen bonding. Okay, so here finally you will get this case breaking of this one. So that here the breaking of this bond and transfer of these electrons O my partial negative. So here O minus catches this hydrogen. So here finally we will get the, so above the plane here OH, and here the ether, that means cyclic ether, also formed above the plane. The stereochemistry is same, but in this case here that cyclic ether below the plane. Okay, the different ethers are formed. So whenever the group is OH or NH2, you will get this compound. Okay, whenever this group is a ester group, that means here ester or OCH3, in this case here that epoxide is formed below the plane. Whenever there is a OH and a NH2, the epoxide is formed in the same plane. If it is a below the plane, this is also below the plane. Okay, so it is. And next here this one. So here Gilman's reagent. Generally Gilman's reagent approaches this one. That means here that is involved in 1,4 addition reaction. Okay, so here 1,4 addition reaction, O minus double bond here CH3. Now here this enolate on reaction with PHCBr. So actually here reformation of the pi bond, this one carries a negative charge. This negatively charged carbon attacks on this bond. Okay, selenium bromine bond. Here selenium, that means here like that means that is a sixth group element. So leaving out the Br minus, so your substitution takes place. That means here selenium and pH, this is a CSA. Now here on reaction with H2O2, okay, on reaction with the H2O2, so this is easily oxidizable selenium, so that is oxidized to the, like this here selenium, here pH, and here plus, here O minus and H2O, the oxidation of the selenium compound. So here CH3. Now here the actually here on this oxide on heating. Okay, this oxide on heating, elimination takes place. So here there is a hydrogen. So this O minus remove this hydrogen, and here formation of the pi bond, leaving out the selenium compound. So here finally we will get the alkene. It is also one of the pyrolytic elimination reaction. That means here finally we will get the pH, Sc and OH. Again, like N oxide, you know that N oxide co-elimination. So similarly, co-elimination reaction, here the elimination reaction takes place. There is a selenium oxide, it is a N oxide, it is a selenium oxide. A selenium oxide and heating will get the alkene. It is a syn elimination reaction actually. Okay, it is a syn elimination reaction. Okay, that means here this, if it is above the plane, this hydrogen also must be above the plane. Syn elimination reaction. Okay, through the cyclic transition state, here elimination takes place, we'll get the alkene. Okay, next this question belongs to the complex compounds. The rate of following redox reaction is slowest when X is, here X is, that means it is octahedral complex, also octahedral complex. Here cobalt plus 3, here cobalt plus 2, in this case cobalt plus 2, cobalt plus 3. That means it is a redox reaction. One is oxidized, one is reduced. Now here this redox reaction is slowest when ligand is, that means here one ligand is missed. So generally here among the 4 ligands, very simple answer this one, a strong field ligand is the NS3. So here if it is a NS3, the replacement of NS3 by these ligands is very that means it becomes a very difficult. Why? Because if X is NS3, there is a strong field ligand. Okay, so strong field ligand cannot be easily replaced by the other ligand. Okay, for suppose this one like cobalt H2O and 6 times, this one reaction with the excess of the ammonia, so that is readily replaced by the ammonia, because here it is strong field ligand NH3. This one has a higher CFSE value, crystal field stabilization energy, than this compound crystal field stabilization energy. This one has a higher crystal field stabilization energy. So that's why here this is stable complex. Okay, when X equals to NH3. So here in this case, you know that another point CO NH3 6 times and here plus 3. Okay. Now here in this case, chromium here H2O 5 times or NH3 here in this case. Here chromium plus 3 means here D3 configuration. So D3 configuration here in this case D6 configuration. Cobalt plus 3 means here D6 configuration. So D3 D6 configuration, this one has a higher CFSE value. So 6 electrons and 2.4 delta naught value. For this one 3 electrons, so 1.2 delta naught CFSE value. So this one has a higher CFSE value. So the replacement of this ligand becomes very difficult. Okay, that means here replacement of ammonia ligand with H2O Cl minus N3 becomes very difficult. Of course, if a ligand is that means actually very weak ligand here is Cl minus. So in case of the Cl minus, that is readily replaced by the other ligands. Okay, just based on the stability we can say the answer. So here whenever ligand is NH3, so that becomes this redox reaction becomes a very slowest. Okay, that's it. Next, here see this one. Here in this case there is a carbonyl group and there is a ester group. Here in this case there are the two electrophilic sites, but here that means these are the two possible products. So compared to this one, here in this case this product is thermally more stable because here CO bond is there, here CO bond is there, here there is no C double bond O bond. So now here on both sides here there is a steric hindrance also. So that's why here this is not attacked by this nucleophile. So simply this nucleophile attacks on the ester. So whenever this one attacks on this ester carbon, so C double bond O here in this case O minus, here NH2 plus and phenyl, here OCS. Okay, then here reformation of pi bond leaving out the ethoxide ion. So that ethoxide ion remove the hydrogen from this NH2 plus. So here NH phenyl is nothing but acyl nucleophile substitution reaction. Okay, the thermally more stable product here 135 degree centigrade is mentioned and 1 hour, that means here slowly formed product, so thermally more stable. So this is the product. Generally here we know that carbonyl compounds on reaction with aniline, okay, we'll get the imine actually C double bond N here pH by the addition elimination mechanism. For suppose here similarly this acid derivatives, for suppose acid halide or for suppose amide or for suppose anhydride, this one reaction with this aniline, so here acyl nucleophile substitution takes place, so we'll get the amide, so RC double bond O NH and pH, acyl nucleophile substitution reaction. Okay, and similarly here this one also on reaction with the hydrazine, so you'll get the RC double bond O NH, here this is NH2. Okay, there's also nucleophile substitution reaction like ammonia, this hydrogen is also like ammonia derivatives, this hydrogen also involved in acyl nucleophile substitution. Okay, that's it. Okay, here next one more question. So alcohol, that means allyl alcohol on reaction with HBr is also allyl alcohol on reaction with HBr. So generally here the point is a very simple reaction, but here the deciding of the major product becomes somewhat difficult. Okay, so that gives some ambiguity. So first of all here the protonation of this hydroxyl group. So here OH2 plus and loss of H plus water molecule. So we'll get the carbocation. This carbocation is stabilized by the resonance. Okay, that's it. So between these two, which carbocation is more stable? This carbocation is more stable. So here, this one attacked by the Br minus. So this is the product actually. Now here, if it is attacked by the Br minus, this is the product. Okay, but here in this case, again here protonation of this hydroxyl group, leaving of this one. So here we will get the carbocation. So just wait, sorry. Okay, here we will get the carbocation, this one. So here it is also stabilized by the resonance actually, pi 1. So here the products are same in both cases, Br, here in this case Br. But here which product is formed? Here highly substituted alkene is formed in a major quantity. That means here 80% of this product and 20% of this product. For this one also 80% of this product and 20% of this product. Okay, thermally more stable alkene is the major product for this reaction. So next here this one on reaction with again here same the loss of water molecules. So we'll get the stable carbocation by the resonance here. We'll get the we'll get this primary allyl carbocation. Now it is attacked by the Br minus. So we'll get this compound. So it is a prenyl bromide. This is prenyl bromide. Okay. So now here in this case, again this is the major product actually. The prenyl bromide is the major product because thermally more stable. Here 3 alpha hydrogens, 3 alpha hydrogens here, 2 alpha hydrogens. So totally 8 alpha hydrogens are there. So thermally more stable. Okay. So from this the formed alkene is less stable. Okay, that is a minor product. That's it. So here in this case, one more reaction I want to say, that is propane diol. This propane diol on reaction with the HBr here, because it is a primary alcohol, there is no formation of the free carbocation. So here that Br minus attacks on this carbon, leaving of the water. So OH here Br. And again same process is repeated, so we'll get the dibromo compound with SN2 manner. Okay, the point is SN2 manner. There is no rearrangement actually. For primary alcohol on reaction with the HBr, SN2 reaction takes place. You know that primary alcohols follows SN2 reaction with the low cost reagent. Like that also here HBr also on alcohols follows SN2 mechanism. Okay, actually there is no rearrangement. Okay, next, this is the one more question regarding the reactivity of the alkali halides in a solvolysis. Okay, in 50% of aqueous ethanol, that means here SN1 reaction. Okay, SN1 reactions, the reactivity of the alkali halides mostly is decided based on the stability of the carbocation. So here in this case, stability of the carbocation tertiary, here carbocation, here in this case allyl carbocation, here also allyl carbocation, but here after rearrangement, we will get the secondary allyl carbocation. So it is somewhat more stable than this case. Now in this case, allyl carbocation, but here tertiary allyl carbocation we will get. Here in this case, pH double bond here plus. Here there is a conjugation with the benzene ring as well as allyl. So by the resonance here, of course, it is a more stable one. The conjugation with phenyl as well as a benzene. That means conjugation with double bond as well as phenyl. Okay, so here in this case, the based on the carbocation stability, here the first one is D is a more reactive. So tertiary carbocation is more stable than the benzyl carbocation. Okay, so here in this case, D is a more reactive, and next one is E, and then here in this case, this secondary allyl carbocation, this is more stable. So here C is more reactive, and then allyl and tertiary butyl carbocation more stable. So A is more reactive, and then B actually. Okay. Yeah, in this case here, the slight change here. Actually here allyl carbocatons and tertiary carbocation is more stable. So A is more reactive than the C. Okay. So you can see in Jonathan Clayton book. So here in this case, this halide is a highly reactive, and next halide this one, and then here tertiary butyl chloride, and then here this allyl chloride, and this allyl chloride is the least reactive. So here in this case, the first of all, the first more reactive alkene is this is the given compound, and first D is more reactive. Next here this compound, and here among these three here tertiary butyl chloride is a more reactive, and then this one, and least compound is B. Okay, that is the reactivity order of the alkyl halides. Okay, so here you can see from the tertiary butyl chloride is more reactive than the allyl chloride in SN1 reaction. Okay, But in SN2 reaction, which is more reactive, that allyl chloride is a more reactive because it is the primary halide, but the tertiary alkyl halide less reactive in SN2 reaction. Okay, that's it. Next here, the reactive order of the given halides with the sodium iodide in DMSO, it means it is a SN2 reaction. So in SN2 reaction, that must be steric free, that must be very simple one. So here among these compounds here, generally here as alpha halocarbonyl compounds are more reactive. Okay, so why? Because these compounds are more reactive. There's a C double bond O, here hydrogen, here a hydrogen. Here in this case, for suppose here hydrogen, here it is a leaving group. That means it is a leaving group, it is a new nucleophile. In this transition state, carbon has a 5 bonds actually. In SN2 transition state, carbon has 5 bonds, so that carbon is a more electron deficient. So that electron deficiency is nullified by the transfer of these pi electrons into this case. Okay, the transition state is stabilized by the pi electrons on the CO group. That's why E is more reactive. Okay, and next here this compound is also more reactive because it is a simple primary halide as well as in the transition state. Okay, here it transition state, here it is a nucleophile. This carbon is electron deficient, so that is stabilized by the conjugation with this lone pair of electrons. Okay, and then here next compound, so it is a allyl halide, it is a benzyl halide. So between allyl halides and benzyl halides, here benzyl halide is a more reactive. And next here why benzyl halide is more reactive than the allyl halide. So here in this case more pi electron density, so that transition state is stabilized by the more pi electron density. So that's why benzyl halide is more reactive than the allyl halide in SN2 reaction. Now here between these two, again here allyl halide is a more reactive because the transition state is stabilized by the pi conjugation. So here finally that is the least reactive. So A, no conjugation, no stability. And next here E is more reactive, D and C and then B. Okay, that's it. So here in this case you can see the relative rate of these compounds here. So it is a that is a butyl chloride, it's a relative reactivity 1. So compared to this one, it is a highly reactive. So because of the conjugation with C double bond over, next here this one also more reactive. Here reactive data of the benzyl halide and allyl halide, you can see here 200 times more reactive than the n-butyl chloride, and here allyl chloride is a 79 times higher reactive than the n-butyl chloride. So here in this case, you have a very simple point. Here methyl chloride and allyl chloride, which is a more reactive, that methyl chloride is a more reactive in SN2 reaction than the allyl chloride because your methyl is a very smaller group, so that's why methyl chloride is a more reactive in SN2 reaction than the allyl chloride. Okay, that is. For suppose here methyl chloride and methyl chloride again more reactive. That's it. Now we generally here this is a more reactive compound. That means it is a suitable substrate for SN1 reaction as well as SN2. Why it is SN2 favorable? It is a primary as well as transition state is stabilized by the lone pair of electrons. But SN1 reaction, that formed carbocation is more stable. That is stabilized by the plus M effect of the lone pair. So that's why it is the most suitable for SN1 as well as SN2. It is also suitable for SN1 as well as SN2 because benzyl carbocation is stable. This one also same, allyl carbocation is stable. And primary halide, so suitable for SN1 as well as SN2 reactions, but it is only for SN2 reaction. Now here this one is not suitable at all for the SN1 reactions. Why? Because carbocation less stable, so it is only most suitable for the SN2 type reactions. Okay, that's it. And next one more question, that is the reactivity order of the alkenes given below with the Br2 in methyl alcohol. So actually here there is a slightly different reactivity order for the this bromine in methyl alcohol. So actually here more substituted alkene is more reactive in alcoholic addition reaction. So here D is more reactive, and now here 1,2 substituted, here 1,1 substituted. So a 2-butene here in this case 2-methyl propene. So between these two here, this compound is a more reactive. Okay, based on the experimental reactivity order here, this is a more reactive towards electrophile than this compound. Between these two here, this one 3 methyl groups are more substituents. Here for these three compounds here same number of substituents. But in this case here 1 substituent is a more reactive, and then we have 2-butene, and between 2-butene, that is a cis and trans. Cis one is the more reactive towards a Br plus alkophile. Okay, that's it. Next here in this case, so this cyclic ether actually. This cyclic ether here, first of all, protonation takes place. So here in acid medium, protonation takes place. So in acid medium, actually nucleophile attacks on the more substituted carbon. But in this case, exceptionally here that attacks on the less substituted carbon. So you'll get the Br and OH. Okay. So there is a major product. For suppose the same type of ether here, two methyl groups are there. So on reaction with the HBr, so first of all, protonation takes place. Now Br minus nucleophile attacks on the this tertiary carbon. Okay. So actually here is a simple one. It is a secondary. The primary is secondary. Primary secondary, which is more reactive in SN2 type SN2 type reactions. Primary. Here in this case there is a tertiary and there is a secondary. So in this case must be, that means SN1 type reaction must be possible. So here Br and this one is a OH. Different that means mechanism based on the substrate here. Okay, even though it is acidic medium, based on the structure of the either in one case SN2 type reaction completely, in another case SN1 type reaction. Okay, that's it. So these questions we will discuss in next part. Okay, thank you for watching.